This video will go through the reinforcement in SLB. We will view how to display the reinforcement results, how the reinforcement results are calculated, and then go through an example from start to finish, looking at the program calculated reinforcement and then inputting our user-defined steel. So the features that we will cover is the design envelope, so the load combinations we design reinforcement for, the material properties as they relate to the reinforcement design, look at the reinforcement calculations, and we'll talk about what is the what are the various terms that we use when we talk about reinforcement in SLB. So the theoretical minimum, the user-defined reinforcement, and the design reinforcement. Then we'll have a look at extra steel and design extra steel using Ast Zones, and then look at the steel rates, so how efficient our design is. Now, a brief overview, the calculation procedure in SLB. In the previous deflection video, we said that the bending moment envelope is calculated initially for the envelope cases, and then we design the reinforcement in step 2. In step 3, we calculate deflections. So this step 2 is the calculation procedure of the reinforcement itself. So initially we calculate the tensile reinforcement required to resist the bending moment. Then we check minimum reinforcement requirements and increase the tensile steel if needed. Next we check crack control for flexure and increase the tensile reinforcement as needed. Then we perform checks for crack control for shrinkage and temperature effects. Now we try to balance this reinforcement in the tensile and compressive zone, so we already have reinforcement in the tensile zone, so any extra steel needed for crack control for shrinkage and temperature is put in the compressive zone. And then finally we check to see if any of the user prescribed steel is bigger than what was calculated in the previous steps. If it is, we use that for the design for the deflection calculations. Looking at the same model that we looked at in the deflection video, we will review the reinforcement results for this particular slab, and then we'll start designing it by inputting some user-defined reinforcement and seeing how efficient that design is. So quickly reviewing the structure that we're looking at, it's a car park slab, a two-way flat plate slab with drop panels above the columns. Hit escape to redraw. As mentioned in the previous slide, the reinforcement is designed for the load combination envelope. Now they are the cases that are set under input load factors and that have envelope ticked in this table, so it will be designed for these two ultimate combinations. If we then go to results and specify one of the combinations, it will be designed for the bending moment for these cases. Or if we want to see the envelope, we hit envelope X. This is the maximum value in the top of the slab, in the X, and in the bottom of the slab. These are the maximum values for those two cases. So these are the ultimate bending moments that our slab will be designed for. So pressing escape to redraw. Next we will have a look at our material properties as they relate to the steel design. So going to material properties, the slab minimum strength is set from this drop down box. So we have a few different options here, and we can specify if we want to design for minimum strength requirements as minimum steel requirements as well. So just for our interest we can switch that off, but that should be on. Beam reinforcement will be discussed in the beam and wide beam video. As mentioned in previous videos, the concrete is input in the slab concrete type table, and all of the various design parameters and those related to reinforcement are input in the slab design type table. So the slab concrete table, this is common between SLB, RCB and PTD, hence why it has its own tab, its own table. And the design type, this is unique just to the SLB software. So what we see here are the default values present in the software when running for the first time. So let's have a look at each one in detail and see what it's doing. So the environment is basically a combination of the environment and the exposure. So this is used for crack control for shrinkage and temperature effects. We can specify the degree of restraint and the crack control type. The program will then calculate the amount of reinforcement in primary and secondary as calculated to section 9 of the code. Note that the program will not allow us to input any combination of inputs that are not allowed by the code itself. And the next thing that we specify is what is the primary direction. So by default it will be in this case it's chosen to be in the X and Y. What this means is that the primary direction is in both the X and the Y. So we have a two-way flat plate slab, so we're allowed to consider both directions as primary. So we don't penalize that secondary direction with larger steel for crack control for shrinkage and temperature. If we were to set it in the X, it would be in the X, in Y it would be in the Y, and then the other direction would be the secondary. What automatic refers to is the program per finite element node will try to determine which direction is primary. So if there's a large enough difference between bending moment in one direction and bending moment in the other, it will set one as primary and the other one as secondary. So that's what happens when automatic is set. However, this may result in basically within the same span, we might have basically the primary direction changing, which we may not want. So for most cases, for two-way flat plate slabs, we can keep it as primary in both the X and the Y. The next input that we specify is the clear cover, so the cover to the reinforcement. And depending on what value we input, the design cover changes. So the design cover is essentially what is used to determine the average effective depth. Now note we use the average cover in both the X and the Y direction. So we'll be conservative in one direction, unconservative in the other. Now this design cover takes into consideration the bar size that we choose. So by default it's 12 mil diameter bar. And we see if we change the size, the design cover changes as well. And this design cover is also taking into consideration the bar laying order. So basically number 1 means laid first, second, third and fourth. Again, there's logic built in, so the program knows if we change this to second, for example, we see the top laying order changes as well. And if we really want to, we could put something a bit unorthodox in there as well. But let's keep it as laid first in the X. What bar angle refers to is the angle at which basically the bending moment and then the reinforcement is designed. So if we have a section of a slab or all of the slab at an angle, we would specify the basically the angle from the orthogonal, and so that basically rotates the X and Y axis by this set angle, and then we calculate the results by that amount. The next input is the minimum steel rate. So currently this is where we input our user-defined steel. Currently it's set to blank, meaning that basically we're running the design for the first time. We don't know what we don't know what steel we'll need to input. So by the very fact that we've left it blank, the program will calculate just the theoretical minimum steel needed to the code. If we were to put in our user-defined steel, it would check these values. But as a first pass, we'll leave this blank and we'll come back later and fill it in. So running the analysis under the Solve tab, we hit Analyze and Design. And then the program will go ahead and design the reinforcement for us. With the analysis complete, we can view the reinforcement results under the Results tab, hit Rio, and then select one direction. So for example, we will choose X bottom first, and the results are displayed as contour lines. We can also display them as colors, but this takes a little bit longer to generate. And if we go back, we'll start looking at the results. We see the range of results displayed here. and we can, instead of going from the main task ribbon, we can alternate between X, Y, top and bottom via these radial buttons. So we'll have a look at X, top and bottom, and we will see some of the various results. So if we zoom in, it's similar to the deflection results. Clicking in the working area displays the reinforcement in millimeters squared per meter at that particular finite element node. Dragging and dropping and releasing selects the highest reinforcement result in that selected area. The way that the steel rate can be displayed is as we've done just now, just with the rate. We can choose to have just the bar spacing, so the specified bar size that we input in the slab design type of 12s at 240, or we can have rate plus bar spacing as well. Other ways that we can display the results, we can perform an integration. So if we navigate to the top and we hit the click integrate with 1 point and distance, going back to the home tab, making sure my settings are snapped to grid, click above a column, and let's specify 3 meters for example. The program will integrate the reinforcement results over the specified length. And again, we can also do manually via 2 points rather than 1 point and distance. So that's done with this button, and then making sure orthogonal is on, we can just manually draw over the top to display a result in millimeters squared. So we just press this button here to clear the integration results. Now, looking at the top steel, we see basically these these green circles. So what this green circle indicates to us is that extra steel has been input here to satisfy crack control requirements for shrinkage and temperature effects. So if we were to see blue dots, what blue dots would indicate is that the steel there has been increased to satisfy crack control for flexure requirements. So this is basically, this is steel that is added in additionally in the tensile zone, because that's where flexural cracks will occur, in the tensile zone. For shrinkage and temperature effects, the cracks extend through the entire section of the slab. So what the program does is, if we go to the bottom, the program's already designed some steel to satisfy, some steel to resist the ultimate bending moment. It has then determined that that is not enough to satisfy the requirements for crack control for shrinkage and temperature effects. So it needs to put additional steel in. It will try to then balance the tensile reinforcement and compressive reinforcement. So it will put any extra steel needed for crack control for shrinkage and temperature in the top of the slab. So in the X direction, it needed 467 bottom and 188 millimeters top. And if we go back to X bottom, we can see these areas where it had higher reinforcement in the bottom, so these spans that basically are working a bit harder. And if we go to the top, we can see it doesn't need any extra steel here. So the theoretical minimum, it doesn't need any steel. What these bold lines represent, this basically represents a line of contraflexure of the reinforcement result. And generally, they should follow roughly more or less the line of contraflexure of the bending moment. So this is sort of where the reinforcement results change from sort of compressive to tensile. And if we zoom right into the drop panels, we can see that the steel needed, we see the green circle, so the steel needed in the drop panel in the bottom X is the minimum needed for crack control for shrinkage and temperature effects. Now this particular example didn't have any steel, didn't have any areas that needed steel for flexure. So now we'll go ahead and start designing the steel and start putting in our user-defined reinforcement. to determine the user-defined reinforcement, we'll look at the reinforcement results. We'll pick basically two sets of reinforcement results that we'll input into the interior parts of the slab and then into the drop panels. So we'll put basically a constant grid of reinforcement that covers the majority of the reinforcement requirements. Then we'll design these spans that need additional steel just to have extra steel locally in these areas. So looking at the X and Y bottom, we see that 467 millimeters squared per meter is needed, typically. So basically N12s at 200 bottom should cover this. And again, looking at the top, so we just have the minimum steel needed for crack control flexure, some small value. So N12s at 300 should more than cover these requirements. Now let's look at the drop panels. So clicking around, we see some value. We see a large peak value happening directly above the columns. Now, due to finite element analysis, this is due to the peak in the bending moment. In reality, this peak will not occur. It will be smoothed out. It will be less at the face of the column. So for the columns, to determine the reinforcement, rather than use this larger value, we'll just integrate over the width of the panel itself. So we press the integrate with 1 point and distance button, make sure we have snap to corner on, press on the column and hit 3 meters. So that's about almost 3,000 over the 3 meters. So N20s at 300 should approximately cover this. We'll do a few more spot checks. So this is looking okay, and we'll quickly check the other direction as well. So within the slab, N12s at 300 should be more than enough, and the drop panels, so 3,000 divided by 3, that should be covered by the N20s at 300. So that should be all right. And we'll double check X bottom as well. So that should be good, and we'll design the extra steel here. Now, how we input our user-defined steel, we go back to the material properties and we go to the slab design type. So just so that we are aware, just so that we know which one is which, we'll label them. So we'll call this one interior, and we'll label this one drop panel. We'll make sure the exposure is the same. Enclosed interior. And we'll set primary direction as both. Same cover, top and bottom. Now the bottom steel will just keep the same bar size in the drop panels here. The default bar size in the slab is okay. We'll set the bar laying sequence the same. Now we chose to have 20s at 300 top. Now, so we just set the bar size. We don't actually input the spacing, we just input the steel rate, and then the program calculates the spacing based off the bar size that we chose. So for the interior slab zone on the bottom, this would be 565 millimeters squared per meter for N12s at 200 spacing, and then 377 millimeters squared per meter for N12s at 300. We'll use the same spacing in the bottom of the drop panel, so we only needed steel for crack control there. And then in the top, we will use that sort of averaged out value of N20s at 300. Next, we need to assign these various design types to the individual slab zones. So pressing OK. How we do that, we'll quickly review what everything is set to. So we go to slabs, color by design type, and we see currently everything's set to interior. We also have drop panel defined, but not used. Pressing this button opens the slab design type table again, which is where we just were. Now we'll go ahead and assign the various properties. So how we do that, we select the individual zones and change the design type property like so. A faster way of doing it would be to select the slabs by type. So we know that all the drop panels are 450 thick, so we'll go to the Home tab, select by type, slab zones by thickness, and we'll select all of the 450 thick slabs. We will then change the design type to type 2. So that is now committed, and we can see all of the drop panels have the drop panel design type property associated to them. Going back to the working area, once we've changed our design reinforcement, our user-defined reinforcement, we see we've lost the results. So we have to analyze again. This time, instead of analyzing again with 1 meter mesh, I'm going to make the mesh finer. Why I'm doing this, if we press Shift-D to show the current 1 meter mesh, I want to have more finite element triangles within the drop panels themselves. So currently there's just one within the at the column center, and then a few more around the column, and then the rest are sort of at this intersection between the drop panel itself and the thinner slab zone. So I want more results within the drop panel, so I will use a 0.5 meter mesh size. With the analysis complete, we'll have a look at our results. So again, reinforcement X in the bottom. We see that there's a few different options available here now that we've put in our user-defined steel. We have design, theoretical, and a few other options. And we'll talk through what each of them is. So if we press theoretical, this should be the same or very similar to the results that we were looking at previously. So this is the theoretical minimum steel to AS3600. So again, clicking in the working area, we just see a value here. So looking at the X bottom, we'll zoom in to have a better look. We see the crack control circles as we did previously in the drop panels, but now we have more of them because we chose a finer mesh. Now let's have a look at the top and we'll see what's going on. Again, similarly in the top of the slab, crack control for shrinkage and temperature effects govern within the slab. However, something a little bit different is occurring in the drop panels. So if we press inside, we start seeing values here of 1047. So basically N20s at 300 millimeters spacing. So previously this was in the order of about 700. That is what was needed in the top of the slab around the drop panels. We averaged it out. But what's happening now is that because in the drop panels we specified an N20 bar size, crack control for Flexure now governs. So the program is telling us that we need 20 spaced at 300 centers in the tensile zone minimum. It sees that there's an N20 bar, so it needs basically N20s at 300, which gives us the 1047 millimeters squared per meter. So that's why we didn't see these blue circles previously in the top of the drop panels, but now we do. And it is the requirements for crack control that have increased the amount of theoretical steel from about 700 to this 1047. So that is where that is coming from. But luckily we put in enough to satisfy that. So that's the theoretical. That is why this value has jumped up. We won't look at the other direction in the Y because it will be similar, but theoretical steel is the theoretical minimum to AS3600, and it should be the default case that's displayed when there's no user-defined steel input. Now that we do have our user-defined steel input, we have another option called design. So we'll look at X bottom and we'll have a look at the various values. So the majority of the screen is white, and we have a few areas here with basically these extra contour lines. So pressing inside the area that is white, we see one set of values in blue, and these areas that have contours, we see some values in red. When in design view, what these numbers on screen represent, basically the number on the left is referred to as the design value. The number on the right is just there for information. Now, depending on the color, this indicates to us whether or not the steel that we have input in this area is adequate. So, looking at the areas where it's blue, the user-defined steel of 565 millimeters squared per meter is greater than the theoretical minimum of 467 millimeters. So the program will go ahead and use this 565 millimeters squared per meter for all subsequent calculations. So for the deflection calculations, for example, these areas that have contour lines and the value is shown in red, the user-defined steel of 565 was not enough. The program will never use less than what is needed, so it will take the required 754 basically theoretical minimum millimeters squared per meter, and we'll use that for all subsequent calculations. So in summary, what the program does when it determines its design reinforcement, it looks at the theoretical minimum and the user-defined steel, and then uses the larger of those two values. So it is basically that is the design value, and it is always shown here on the left. If we don't like this particular view, we can just switch this off. So this 1 brackets 2, and if we press inside these areas now, we just see the design value. So that is in the X. For the remainder of this example, we'll just look at the steel in the X direction. So looking at these areas, if we want to see just what the extra steel is, we can toggle the extra on and off. The contour line should be the same, but now when we press in the working area, it tells us that we need 0 extra in these areas and just the extra steel in these areas that have the contour lines. Zooming into the drop panels, we can see that we have some extra steel that is needed within the drop panel, but just for these few. And we know that we need that extra steel if I press Shift E, because it occurs on quite a few of the finite element nodes within the drop panel. So that's why we made the finite element mesh finer, so that we could capture this situation. So one option would be to increase the steel in all of the drop panels, or make a separate design type and increase the steel just in these drop panels locally that need the extra reinforcement. So hitting escape just to redraw, going back to results reinforcement X bottom, we'll go ahead and design the extra steel in the bottom. So how we can do this, we can define these areas with different geometry lines, or we can use a tool called the Ast Zone, so we don't have to draw the geometry line to specify separate design types, which can start getting to be a bit fiddly. How we use the Ast Zone tool, extra steel must be switched on, otherwise the tool doesn't work, and the button here is next to reinforcement, so Ast Zone. So if we press this, make sure our snap setting is snap to grid, which it is, so we can see that from the green square and the mouse icon. We hit one corner and hold Shift and define the extra corner. So based on the area that we've defined, the program has designed the extra steel for us. So showing the reinforcement in the X bottom, we can see it integrates over this area and has designed N12s at 490 extra on top of the N12s at 200 that we've defined. Now the Ast zone is just an integration zone, so you may have noticed that we did not lose the results when we drew this. And we can start modifying the values to something a bit more reasonable by selecting the Ast zone, selecting its perimeter, and then changing the values. The program will not let us put something in that is less than what is required. So if we put something less steel in, it tells us it's an invalid input. But if we put something in that's reasonable, so for example 12s at 400, so basically every second bar in our grid will lay an extra N12, it allows it if we hit enter. So now we have the N12s at 400 in this area. We would similarly repeat the process for these zones and also for the Y direction. So in summary, we designed the extra steel in these areas with the contour lines with the Ast Zone tool, and the extra steel that is needed in these drop panels, which we didn't show, can be defined by specifying a different design type in these drop panels, so selecting them, changing their design type to something else, and then inputting an additional design type with extra steel so that these areas can work, but not shown in this example. Hitting escape, we'll have a look at the reinforcement in the top. So looking at the top, we see a few areas that have extra steel around the intersection of the drop panel and the thinner slab zone. Pressing these values, we see a very small value. So basically, we can ignore this because what the software is doing, it is essentially taking the average thickness of the slab and the drop panel, trying to average out the reinforcement and seeing that what has been put there is not exact. Hence, it is giving a bit of extra steel in these areas. So we can ignore these small values. And similarly with these peak values, as we did previously with the theoretical value, if we average that out over the width, we would find that the steel that we put in of N20s at 300 would be okay. So again, if it's just a single peak value like it is at this column, we can ignore that. If we wanted to put in extra bars directly above the columns, rather than using the Ast Zone area tool, we can use this Ast single bar tool. These tools are also available under the modeling section of the Home tab. So we make sure snap to corner is on, make sure define with 1 point is on, and we press the single bar, click above the column, and we'll make it 5 meters long, say. Then we can select the bar and modify it. So for example, we could put 5 extra 20s at 200 spacing, and then the program shows us the extents over which those bars will be laid. Now let's imagine we repeat that process, designing the extra steel top and bottom X and Y. We can then view the user-defined reinforcement to see if we're above or below, see how efficient our design is. So we need to display the results to do this. So for example, X bottom, we go to Tools, check User-Defined Reinforcement, and check Above. So we see some dots and squares, circles displayed on screen. If we double-click in the Properties tab here and pull the notepad across, we can see what each of these mean. So basically the dark blue, light blue squares, we're between 10-50% extra, dark blue we're more than 2 times extra. And we can see that it's considering the user-defined steel that we've put in the Ast zone as well. Now we could also check similarly below, but we know that just by looking at this we can see that these circles indicate we don't have enough steel in these areas. Also the contour lines show this too, so we won't show this in this example. Finally, once we've put in our user-defined reinforcement, designed extra steel using Ast zones in single bars, defining extra design types as needed. So for example, for these drop panels, we can check our final steel rate. So pressing the steel rates button, we see the total steel that we've put in, considering all of our user-defined reinforcement Ast zones. And then basically it's increased by the program by 10, 20, 30% to consider hooks, laps and cogs. So the software doesn't detail the steel, we don't consider lap length, basically all the detailing through steps and folds, so we just apply this factor. In this video we only looked at the X direction, but we would follow a similar process for the Y direction, top and bottom as well. In summary, what we did, we checked the theoretical minimum reinforcement required to the design code. Based on that theoretical minimum, we input some user-defined steel using slab design types. We reran the analysis and then checked for extra reinforcement. Extra reinforcement was either input using additional slab design types or designed using Ast zones, and Ast zones with single bars. We then check to see how efficient our design is using check user-defined REO and check steel rates. Then if we wanted to, we could further refine this design. So all of the slab design and detailing is done within the SLB software. This concludes this video. Thank you for watching.